Yeah. So it's a pleasure to introduce Luna Lomonaco from IMPA, Brazil. The title of her talk is Rational Map, Kleinian Groups, and Correspondence.
Thank you very much for the presentation and for the invitation. When I was a little kid, I was very, very much fascinated by India. So far away, so different, so mystical in my imaginary. I remember a friend of my mom who went to India for honeymoon, and for me it was something like, wow, she went to India. It felt like she went to Mars. And India was the destination of my first intercontinental trip when I was 20 years old. And since then, it has a very special place in my heart. So I'm very happy to be here today. And today I will speak about how the world of rational maps and Kleinian groups can combine in a correspondence. This is, as Misha anticipated, maybe the holomorphic counterpart of his talk. And I should say that most of what I'm going to say is based on joint work with Sean Bullitt from Queen Mary University of London, and other things of work that Sean did when I was at kindergarten. So it's a bit of a long story. And I apologize with the expert. I will start gently for students. So if we iterate a rational map on the Riemann sphere, this gives a partition of the Riemann sphere into two completely invariant subsets. The set of points where the dynamics is easy, as I would say, they all do the same things. Where the family of iterates is epicontinuous on a neighborhood, which is called the Fatu set, and it's complementary. Interesting. Called the Julia set. By definition, the Fatu set is open. Both sets are completely invariant. By definition, the Fatu set is open, and the Julia set is closed and compact. And the Julia set, if it is not the whole Riemann sphere, it has empty interior. And if the rational maps has degree at least 2, the Julia set is non-empty. It is a perfect set, and is the closure of repelling periodic points, orbits. And I mean, it has a lot of other nice properties, but just to name a few. Now, changing word, let's consider Kleinian groups. Again, on the Riemann sphere, Kleinian groups, as everybody knows here, are discrete subgroups of PSL to C. And their dynamics on the Riemann sphere, again, gives a partition of the Riemann sphere into completely invariant subsets. One is the limit set, which is the set of limit points, which is a compact and invariant set. And if it is not the whole Riemann sphere, it has empty interior, and it has either 0, 1, 2, or infinite points. And if it is infinite, it's a perfect set, and is the closure of fixed points of loxodromic elements of the group. And the complement set is called the ordinary set or the regular set, and it's open and completely invariant, and it can be shown that is the set of points in the sphere where the elements of the group form a normal family. Okay, so how I hope to have suggested in these first 2 slides, these 2 words of iteration of rational maps on the Riemann sphere and Kleinian groups on the Riemann sphere are not so different. The action of both objects gives a partition of the Riemann sphere into 2 completely invariant subsets, the set of normality, an open set, which in the case of rational maps is called the Fatu set, and in the case of Kleinian groups is called the ordinary set, and the complement, which in case of the rational maps is called the Julia set, and in the case of Kleinian groups is called the limit set. And these sets have similar properties. And this, as Misha remarked Monday, is something that probably Fatou already realized. And it's so that these two words are not so different. And Sullivan realized also in the 80s when he developed what is being famously known as the Sullivan Dictionary, which is a dictionary between the two words where definition, conjecture, and theorem are translated from one word to the other. Here in this talk, we're interested in knowing how these two words can be combined together. So the question is, can these two words be united? What I mean with this, can these two words coexist in a single object? If this is the case, we will call this object a mating. A mating, roughly speaking, between object A and object B is an object C, which behaves like A on a completely invariant subset of its domain, and as B on the complement. They do exist in the words of rational maps and in the words of Kleinian groups. Actually, they started in the word of Kleinian groups. And the question here is, can we mate a rational maps with a Kleinian group? This question clearly has, I mean, if you wonder this, you start thinking, okay, a map is not a group and a group is not a map, so we need an object where the two things should be combined. And then if this is possible, you need the dynamics on the boundary, I missed a third hand, on the boundary between the group and the map to combine. So are these things possible? First problem, is there an object that can be a mating? And yes, there exists an object that can be a map and that can be a group. And here we enter the world of holomorphic correspondences. Holomorphic correspondences on the Riemann sphere is a multi-valued map f from zeta and w, which is defined by the zero of a complex polynomial in zeta and in w. And we are interested in these objects because we can write a rational map as a correspondence. If my rational map is P over Q, you just take as the polynomial that kills the map. So W, Q of zeta minus P of zeta. This becomes an n-to-1 correspondence. And if you have a Kleinian group with, let's say, 45 generators, A zeta plus B over C zeta plus D, you just take the polynomial that kills generator by generator. So the product of this. Just to have a feeling of what is a correspondence, in this talk we will be mostly interested in two correspondences. So if we have a chalk there, if we have a polynomial of degree 2 in zeta and w, its zeros defines an algebraic surface. And we can consider the projection in the Riemann sphere, where my zeta lives, the one in the Riemann sphere, where W lives, and my correspondence will be the object that associate to each zeta other 2W in this case. For each zeta, you have 2W here upstairs that kill the polynomial. These are going to be your images. And for each W, you have 2 zeta upstairs that kills your polynomial. And this will be your preimages. And you start iterating this thing, and the at the third iterate, it becomes a big mess, but it's interesting because, again, we can write both groups and maps as correspondences. So the hope is that we could find a correspondence that can be both at the same time. But before going there, let's consider the second problem. Let's assume I have an object, then on my boundary, this object, where is a group and where is a map, they need to coincide. So does the dynamics of some map on the boundary of an invariant Fatu component agrees with the dynamics of a group on the boundary of an ordinary set? And the answer is yes. At least in the case of the modular group and the map zeta square. The modular group is the Kleinian group generated with these two maps. H zeta is zeta plus 1, and beta of zeta is zeta over zeta plus 1. Here you see a tessellation of the modular group on the upper half plane. In the lower half plane, you will see exactly the same. So out of economy, you usually represent just the upper half plane. And the limit set is the real line, the extended real line. And here you see the map zeta square. Its Julia set is the unit circle. All the points with modulus less than 1 under iteration goes to 0. So the unit disk is a Fatu component and the complement also. And this map on the unit circle, on its Julia set, behaves as the Dublin map. And there is a map, the Minkowski map, that Misha presented us on, introduced us to on Monday, which is a homeomorphism between, well, I mean, this is a modification of the Minkowski map. We go from the positive real line to 0, 1, which is the homeomorphism, which sends a real number written in continuous fraction expansion to a real number written in binary. So if the continuous fraction expansion is x0 plus 1 over x1 plus 1 over blah, 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 the image is not followed by x0 copies of 1, followed by x1 copies of 0, followed by x2 copies of 1, and blah, 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 blah. And these maps conjugates the action of the generator of the modular group on the negative real axis with the Dublin map, and on the positive real axis with the Hastings map. What does it mean? Why am I telling you this? Well, I'm telling you this because, do I have also colors? Yes, I do. So here we have our upper half plane with the modular group, alpha and beta. Here is 0. And on the negative real axis, the Minkowski map conjugate the dynamics to the dynamics of zeta goes to zeta square. Well, on its Julia set, which is the Dublin map. Here we have x goes to 2x. And on the positive real axis, this map conjugate the dynamics with the dynamics of the inverse. Zeta goes to square root of zeta, which is x goes to x over 2 on the unit circle. Yes, and it's a good point. When I'm saying conjugate like this, I'm a bit lying because the negative real axis is not invariant under alpha, for example. So all of this is slightly more complicated. To be honest, you have 6 commutative diagrams between one between alpha and the doubling map on the x less than -1, and then a piece between these and these, and you have to do it step by step, but yes, they are all commutative diagrams. So yes, it becomes 4-bit equivalent. Okay. So why I'm saying this? Because you can wrap the modular group, the upper half plane, like that, around 2 copies of the unit disk, with the dynamics of zeta square on one side and the dynamics of zeta square on the other side, and the dynamics would agree on the boundary. So a mating is possible. And as expert knows, when we speak about the zeta square, we don't really speak just about the zeta square. It's a bench of maps. And here we speak about quadratic polynomials and the family pair 1, 1. So as you know, tell us, we can consider the quadratic family zeta square plus c, which is this family of quadratic polynomials on the Riemann sphere. For each of them, infinity is fixed and is super attracting. It attracts points very fast. And it has a basing of attraction, which is AC of infinity. And if you're very close to infinity and you start iterating your point, the plus c is not really important. And actually, there is a conformal conjugacy between the dynamics of your map near to infinity to the map zeta goes to zeta square. And you can define the field-Julia set as a set of points with bounded orbit, and the Julia set is its boundary. And as you know, say the field-Julia set either is connected, either is a Cantor set. And in the case it's connected, this conjugacy extends to the whole complement of the field-Julia set. And if the Julia set is locally connected, it descends to a semi-conjugacy on the Julia set. Here there are some field-Julia sets, some are connected, some not. And the connectedness locus of the family is the famous Mandelbrot set that we saw already several times in this workshop, is this set. So when we fit here the map zeta square, we could have started with any quadratic polynomial with connected and locally connected field-Julia set. But there is more, because there is another family of maps, which is, okay, quadratic polynomials. For every quadratic polynomial, infinity is fixed and super attracting. Now you can decide to keep infinity fixed, but parabolic. So it attracts on one side and it repels on the other. And if you do this, you end up with this family of maps. Pair 1, 1, which is the family of map zeta plus 1 over zeta plus a with a complex. Actually, this is a modular space. It's up to, this is a family of conjugacies classes. It's up to the conformal conjugacy. A and minus a will be in the same conjugacy class, but it doesn't matter. For everybody in the family, infinity is fixed and parabolic. So again, you can define the set of points with bounded orbit as your field-Julia set. And here there are some examples. And on the parabolic basing of attraction, your map is conjugated with this Blaschke product. And on the circle, this Blaschke product is topologically conjugate with the map zeta square. So you could have start here with a guy in this family with connected and locally connected Cis-Julia set. It would work. By the way, this is the connectedness locus of the family, the parabolic Mandelbrot set. And it's homomorphic to the Mandelbrot set. They look more or less similar by a work of Karsten and Pascal Koch. One. We won't be using practically the Minkowski map as in the work of Misha and Sabia and collaborators. So we won't be interested in the regularity of these maps. This is, for us, a motivation. That map exists, so a mating is possible. So we can continue. We're not being crazy. We can continue in our investigation. And all of this has been realized by Sean Bullitt and Chris Penrose in '94, when they saw that this map is a conjugation. They realized that a mating is possible, and they realized that correspondences can be both objects, so a mating is possible in a correspondence. And then they cooked up this family of correspondences. It's a family of two holomorphic correspondences, were given by this expression. And they proved that this is the picture of a limit set for this family, which I will define what a limit set is in 2 slides from here. But you can see here that it seems to see 2 copies of this field Julia set. And outside, the tessellation of the modular set. And they proved in '94 that this is actually the case for all A in this interval. And now you can wondering, what did they dream for come up with this family? Well, you can construct that family by surgery between a quadratic map and the modular group, but this is not what they thought at the time. What they thought is the following. Well, let's say that I want the modular group outside on an invariant subset of my domain. And the modular group is the Kleinian group generated by alpha and beta, but I can also take different generators. I can take sigma of zeta, it's -1 over zeta, which is an involution. And rho of zeta, which is -1 over zeta plus 1, which is order 3. And if you write it like that, it becomes clear that the modular group is free product of cyclic group of order 2 and of order 3. So when you try, you can write it as a correspondence in this way, composing the delete covering correspondence of the cubic polynomial zeta goes to zeta 3 with an involution. If I have a degree 3 polynomial, generically, 3 different points to the same guy. The deleted covering correspondence is the correspondence that exchanges the fibers. So it will send this guy here and here. So this will be my order 3 element. And then you compose it by an involution, which will be your order 2 element. This is what they were thinking about. Yes. Thank you. And this is actually the picture of the modular group written as correspondence. This will be the linear, the real line that becomes a circle, and you see the modular group acting here outside and here inside. So you write it like this. Then I start thinking, okay, but I want a correspondence which is not just the modular group. I want a polynomial inside. For this, I need a free critical point for a polynomial do all the different things that it does. And so they cooked up this family, which is written exactly in the same way, but the polynomial is now zeta 3 minus 3 zeta. And you change coordinates, and you end up in this family. Okay? And you saw that here we have a parameter, which is the fixed point of the involution. And moving the parameters, you will see all these pictures. For how the family has been cooked up, there is a topological disk. In this picture, the right half plane, which is forward invariant. This line is sent to this line and to this line. So everything here is mapped 1 to 2 here inside, which is mapped inside and inside and inside and inside. And this guy is called the forward limit set. This is the fundamental domain for the involution. So since there is an involution, here you have the opposite. So you actually have a degree 2 honest map that goes between this topological disk to this one, which will be a pinched polynomial-like mapping. This map, this line is sent here, and this map, this line is sent here. And here you see this, if you take the intersection of all the preimages of this disk, you get the backward limit set, and together they are the limit set. By construction, this point, which is a fixed point for the involution, is a parabolic fixed point, and it's the point where the forward limit set intersects the backward limit set. And you can make computation to see that it's parabolic, but you can also see the dynamics. Here you do pop, and here you do pop. Okay, and here you see a lot of limit sets. All of these are connected. This is disconnected. And this is the connectedness locus of the family, the set of parameters for which my limit set is connected. So looking at picture, it's straightforward to conjecture that this family of correspondences contains a mating between the modular group and every quadratic polynomial with connected field-Julia set, and that the connectedness locus is homeomorphic to the mandelbrot set. And this has been the dynamical conjecture has been proven true for a lot of parameters in the mandelbrot set, but they never managed to bring everybody home because this point is parabolic. So the way they were doing it was splitting this point in two, using polynomial-like mappings, and then come back for everybody. And this suggested that maybe you need to deal with the parabolic point. And this is what we did. And we defined a mating between a parabolic quadratic rational map of per 1,1 and the modular group as a 2-2 correspondence, such that there exists an open invariant subset of the sphere where both branches of my correspondence are, where the branches of my correspondences are conjugated to the generators of the modular group acting on the upper half plane. And on the complement, you have two compact sets that touch on the parabolic fixed point. And on one, you have a hybrid equivalence between the correspondence here and PA. And because of the involution, and on the other side, you have hybrid conjugacy between the branch that fixes it and the inverse of your quadratic rational model. And we prove that for every parameter in the connectedness locus, this family is a family of matings between some PA and the modular group. And then you can look at parameter places, parameter spaces. And we proved that there is a dynamical homeomorphism between the connectedness locus of the family and the parabolic Vandenberg set. Dynamical means that this point, which dynamically is this, goes to this point, which dynamically is this. And here I have hybrid equivalence between a double pinch neighborhood of the backward limit set and a doubly pinched neighborhood of the Julia set. And you see the representation by pictures. I mean, these are the center of the period 2 components, this one of the period 3. And thanks to Carsten and Pascal, this implies that actually the conjecture was true. What we call the modular Vandenberg set is actually homeomorphic to the Vandenberg set. Thank you. You can extend this homeomorphism to a neighborhood minus a neighborhood of the root. Yes, and actually you can prove that outside is quasi-conformal, and on interior, it's conformal. But you don't have compactness. I mean, you can't extend that these things don't exist here. Yeah, so I mean, you can't go all around. This sits on the boundary of what is called the Kleinian combinatorial locus, such that you can start doing all those things make sense. So you don't have compactness. And life without compactness, it's a difficult life. Okay. Just 2 words about the proof of all of this. I promise I will be brief and gentle. Both results are based on the existence of lunes, since I'm called Luna. No, it's for doing surgery. We said before that we have a pinched polynomial-like map between this set and this set. But here we have cusps. And cusps we don't like. If we want to prove that here you have a member of the family pair 1, what you want is to replace everything here outside with the bending of attraction of the parabolic fixed point. And you want to do it by surgery. Or you have a smarter way, but I mean, I wanted to do it by surgery. And for doing surgery, cusps are not very nice. So everything actually boils down, well, not everything, but I mean, the main technical step, it's proving that this guy is inside a lune, something that makes an angle here strictly less than pi. Then your pre-image will be here inside, and here you will have space, and you could do surgery things. And another important thing is that constructing here invariant, forward invariant arcs. And here you can just take 4 cycles if you want. And once you have this setting, then you're in business. For the dynamical theorem, you can just attach outside the Basing of attraction of infinity 1 by 1. This thing can move, so you're happy. If you want to prove the parameter plane theorem, then at least I wanted to use holomorphic motions and all the Duody-Hubbard machineries. And for this, you need these things to move holomorphically. And this was very difficult to prove. It boiled down at proving that the parameter plane is contained in a Lune, and we needed a Jacobs inequality for this. It was all very involved. It took a lot of years to prove. But then we managed. And then you can prove the parameter plane result. Well, you still have the problem that you don't have compactness. So even when you have your nice holomorphic motion, in order to prove that on the other side, you have the whole connectedness locus. In order to prove that you have a map from all the compact guy to all the compact guy, it's a bit involved. I mean, you have to bring home limbs by limbs in order to say that you have surjectivity. It's not easy peasy, but you can do it. Since I'm not so bad with time, let me just say that you have 2 ways for attaching the Basing of attraction of infinity here outside. In my PhD thesis, per 1-1, if you have the field Julia set of per 1-1, a PA, and you take a neighborhood of it, if this is the parabolic fixed point, you will see that the pre-image will be something like this. And then you can cut the expanding part from the parabolic part with invariant arcs. And this is a parabolic-like mapping. And if you have a parabolic-like mapping, then you have a member of per 1-1. I developed a surgery. This was my PhD thesis. When you apply this thing here, if you do it 1 by 1, it was very fast, very easy to attach here directly the attracting petal to turn this guy into a parabolic-like map. And then you apply my thesis and you're happy. If you want to do it with parameter, you can. But if 1 by 1, this surgery is something very, very easy peasy, you can actually write down the quasi-conformal map. If you want to do it with parameters, suddenly it becomes extremely technical, and it became more worth it to just attach directly the Basing of attraction of infinity, doing a surgery similar to the one that of parabolic-like maps. But it can be done in both ways. Actually, we did it in both ways, and we have the same result in archive written with the 2 different proofs. Okay. I won't say how you prove that outside you have the modular group, but I will just say that this passes by constructing what will be a butcher map from this open set to the upper half plane, which conjugates the branches of your correspondence with the generator of the modular group. And I colored to say what goes where. I mean, this thing, this domain will go here. This will go here. And this, what is colored pa here, and pa. I found it very, I don't know, the first time I put the colors myself, I found it very visual enlightening, and so I wanted to share this with you. But I want to give the proof of this because it's a little bit involved. Okay, but once you have a butcher map between this open set and this, then you can build you can use it to build some of the theory, dynamical theory that Doherty-Hubbard did for quadratic polynomials. The butcher map for polynomials is very, very used for proving several things. And here you can use that butcher map. What I mean that you can pull back the structure of the modular group. You have a lot of structure here to your dynamical plane. For example, here you have periodic geodesics, geodesic that after a finite number if you consider a word in alpha and beta, it has two fixed points, and the periodic geodesic will be the one that the geodesic between the two fixed points. And you can pull it back here by your butcher map. And you can prove and display in our theory more or less the role that external rays play for quadratic polynomials. In particular, you have that periodic rate length for quadratic polynomials, and here we have that periodic geodesics length. And for quadratic polynomial, you have that every repelling fixed point is the landing point of a periodic ray. And here we can prove that every repelling periodic point is the landing point of a periodic geodesic. This was very hard to prove because in the quadratic polynomial case, you have infinity that is very much used when you want to do your modulus inequality, blah, blah, blah. Here we don't. So it passed through multiplier of Sturmier words. But you can do it. And then you can use it to prove a Jacobs inequality. These are done for quadratic polynomial, and we can do it in our case. Actually, we have a stronger one at the first level, which very roughly means that the Jacobs inequality very, 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 very roughly says how much the limbs shrink, how much these things attached to the main cardio can be, how big. And the fact that our is stronger, very, very, very roughly speaking, says that these limbs shrink with respect to the main cardio more than in the polynomial case. Very, very, very roughly. They shrink so much. Okay. And I should mention that recently there has been a lot of work in this area of matings of maps or anti-holomorphic maps and groups. Misha showed us very, very beautiful works with a lot of collaborators. I brought some here, but the group is very productive. This was in the anti-holomorphic centi. Sabia and Mahan produced matings between rational maps and Kleinian group in the holomorphic setting, passing through Bowen series maps. They first reduce the group to a map, and then they make the map. It's very smart. And I should also mention that this family of correspondences has been studied from an ergodic point of view from De La Parra, which is a student of Juan Riviera Letelier. And in general, correspondences, families of correspondences have been studied recently under an ergodic point of view by Dean and Lucas Kaufman and other people. And okay, I started speaking about rational maps and Kleinian groups, and so far I spoke about the rational maps and the modular group. Let's change group. So I said before, the modular group can be viewed as a free product of cyclic group of order 2 and of order 3. And you can consider all the faithful discrete representation of this free product. And this will be their discreteness locus. This is the set of the parameter here is the, how is called? The ratio between the fixed points of, no, it's not the ratio, between the two fixed points of the order 2 generator and the order 3 generator. The complex ratio, how you say it. Thank you very much. The cross ratio between these. And this is the parameter here. And Sean and Bill Harvey proved that actually you can mate any of this, or any representation in the interior of this guy. So any representation with disconnected limit set with any quadratic polynomial. And the mating will end up in this 2-2 family of holomorphic correspondences. Just to be clear, this is for k equal 1 is the family I showed you before, and the modular group is this cusp here. They are both complex, yes. And if k is 0, this gives you C2, C3, gives you these guys. I don't remember the parameter A for which actually you have the modular group, but yeah. And Miguel Ratis, my PhD student, proved that this mating is actually continuous. So you can move continuously in this cross product if you want, changing the correspondence. And here I show some pictures. Here you see inside you have 1, 2, 3, 4, 5, 6, a guy more or less here. And outside you have a group that it's more or less here, is close to the modular group. Here you have a polynomial close to -2 and a group again here close to the cusp. And here suddenly you're in the disconnected, the both disconnected set. You're more or less here times here. And what we're studying now is we have continuity between the Mandelbrot set and this discreteness locus, the interior, and we're looking what happens when you go to the boundary. But the question is pretty much involved because, I mean, you should imagine that, I mean, above each representation, you have morally a Mandelbrot, but above the cusp, you have a parabolic Mandelbrot set. So for moving to the cusp, you just don't go between quadratic polynomial and per 1, 1, but you're also moving a group together. So it's a little bit of a mess. And this is the easiest boundary point you can get. The slice here is much more involved because the group here interchange the upper half plane and the lower half plane. And here, the other cusps, you have circle packing representations. So it's all a word there. But this said, you can generalize this in degree D. Yes. In what sense? Yes, well, actually, I know that it looks like that, but this is the cauliflower. I actually think this is why it looks so much as the cauliflower. I guess it is, but I don't know. I mean, we're looking at the single cusps. We're very far away to try to look the whole boundary. We have the open set inside, and we're looking at single points on that boundary. But yeah, you can generalize this in degree D. I mean, this guy, well, this guy I just told you that is the cauliflower, but imagine that is the discreteness locus that I was claiming it was. The discreteness locus of faithful representation of cyclic groups of order 2 and order 3, then you can consider cyclic group of order 2 and order D or Q. And we're working on matings, these guys, with polynomials of degree Q minus 1. And looking the continuity in the multibrod case, in the unicritical case. But this is very much work in progress. But then you can wonder what happens to the limit. What happens when Q goes to infinity? And actually, this is something that we already have. Well, I mean, Sean already did when I was in secondary school, probably. That when Q goes to infinity, the limit group can be mated with a transcendental map and obtain a infinity to infinity holomorphic correspondence. This is very, very roughly speaking. I mean, to make this statement precise, it should take a while. So I mean, you have to make sense of what infinity algebraic thing means. But I mean, these things exist. That there is a paper, I think is in ergodic theory. And okay, this, if you look here inside, you have hyperbolic guys. When you have the discreteness locus, where you are inside the discreteness locus, so you can make them with polynomials. I mean, here again, these guys are mated with these guys, and the cusp is mated with parabolic quadratic polynomials. And then you can look the same here in the cusp, in the parabolic case. Yes. We are trying in the quasi-conformal, yes, because it's hyperbolic with hyperbolic. I mean, if you send hyperbolic to hyperbolic, you're happy. Parabolic to parabolic, you're happy. More or less, but you're not so sad. But when you want to change, then this is all hyperbolic. And this is all parabolic. So you can look at the parabolic part. You can consider the modular group this time as a Heck group. So the group generated by the involution zeta goes to minus 1 over zeta, and the map zeta goes to 2 zeta cosinus of pi over 3, which is 1/2. So this is 1. And then you can generalize at the Heck group. Actually, the modular group will be Heck group of degree 3, and you can look D plus 1. And then you can think how to map them as Heck group of degree 3 are mated with quadratic rational maps. These guys of degree D plus 1 should be mated with degree D rational maps, parabolic rational maps. Naturally, you can consider the set of the degree rational maps with a parabolic fixed point having a simply connected parabolic basing of attraction, and conformally isomorphic on the basis to this Blaschke product. And we're working with Sabia and with Misha now, improving that if you have a map here, then you can produce a DD holomorphic correspondence, which is a mating between this map and the Heck group. And this is with Sean, we came from the correspondence side, while Misha and Sabia worked a lot in the anti-holomorphic setting, and starting by considering writing the group as a map, a Nielsen map, and then going from there. And actually, we came up in the group with 2 equivalent proofs using the 2 different settings, which is super interesting because we can see how these 2 settings can combine together, the differences and the similarities. And it's a very nice theorem, I think. But yeah, and this is everything I wanted to tell you. So thank you very much for your attention.
Thank you very much for a very nice and energetic talk. It was very interesting.